What if the biggest particle accelerator ever built has been accidentally throwing away the most important data in the history of physics? Not because of incompetence, not because of budget cuts, but because nobody knew what to look for until now. The Large Hadron Collider sits beneath the Swiss-French border in a tunnel so long you could fit Manhattan inside it twice. It smashes protons together at speeds so close to the speed of light that the difference is almost philosophically embarrassing. And for over a decade, scientists have been firing it up, watching particles explode and waiting for something genuinely new to appear. Something that breaks the rules, something that explains the 27% of the universe we literally cannot see. That something is dark matter, and we still have no idea what it is. Now, before you roll your eyes at another dark matter video, stay with me, because what's happening right now is different. There's a genuine shift in how physicists are thinking about this problem, and it centers on one particle that already changed physics once before, the Higgs Boson. The particle, the LHC, was actually built to find. Discovered in 2012, Nobel Prizes handed out, champagne popped, physicists celebrated, and then immediately got back to work, expecting even bigger discoveries to follow. Those discoveries never came. If you're into physics, space, or just watching humanity slowly decode the universe, this channel is where that conversation lives. Stick around and subscribe. New episodes drop regularly, and trust me, the rabbit holes only get deeper. So back to the LHC. After finding the Higgs, physicists cranked up the energy, expecting a parade of new particles to show up. Supersymmetric particles were the big hope, exotic heavy cousins of the particles we already know, which would have explained several unsolved problems simultaneously and handed us a solid dark matter candidate in one shot. The collider ran. The energy climbed. The new particles never materialized. At this point, the machine is approaching its maximum designed energy output, and there's no realistic expectation of anything new appearing before it hits that ceiling. Which sounds like a dead end. But here's where the thinking gets genuinely interesting. For years, the search for dark matter operated under a quiet assumption that dark matter is probably just one particle. A single exotic addition to the particle zoo we already know, drifting invisibly through the universe, occasionally passing through your body right now at a rate of millions per second without you feeling a thing. Researchers hunted for it. Experiments were built specifically to catch it. The sterile neutrino was one of the most promising candidates, and it was recently ruled out as a viable simple solution. The window for dark matter being a lone particle is closing fast. But what if that assumption was wrong from the start? What if dark matter isn't a particle? It's an entire parallel world of particles. A complete shadow version of the physics we know, with its own quarks, its own force carriers, its own equivalent of atoms. All of it completely invisible to us, not because it's hiding, but because it genuinely doesn't interact with any of the forces we use to see things. No electromagnetic charge, no color charge, no weak force interaction, just matter existing in a parallel layer of reality, threading through the same space we occupy, detectable by gravity alone. Physicists call this a dark sector, and if it exists, it changes everything about how we look for dark matter. Here's the key question. If the dark sector has no interaction with our forces, how would we ever know it's there? The answer is something called a portal, not a science fiction portal, a specific kind of particle interaction that allows energy to flow between the standard model and the dark sector. There are only a handful of candidates for what those portals might be, and the most promising one is the Higgs boson. The Higgs field is the simplest type of quantum field that exists. While other fields in the standard model carry complex internal symmetries, complicated knots in the fabric of quantum reality, the Higgs field is comparatively clean. That simplicity is exactly why it couples so broadly to other particles, granting them mass in the first place. And that same simplicity means it could couple to dark sector particles too. The Higgs boson, the particle produced when the Higgs field gets briefly disturbed by a proton collision, could literally transform into dark sector particles. It would be the doorway between our world and theirs. This is enormous. Because the LHC cannot make supersymmetric particles, they're probably too heavy, but it absolutely can make Higgs bosons. It makes them constantly, which means the portal to the dark sector might already be opening millions of times a day inside that tunnel in Switzerland, and we've been unknowingly ignoring every single instance of it. Here's why. When protons collide at the LHC, the amount of data generated is genuinely staggering. Roughly 600 million collisions per second, each one producing a spray of particles that light up layers of detectors like a fireworks show. If you tried to record every single collision in full detail, you'd need to store around a petabyte of data every second. That's not possible. So, the experiment uses what's called a trigger system, a near-instant filter that decides in a fraction of a second which collisions are interesting enough to keep and which ones to discard forever. The triggers are designed around what we expect to see. A Higgs boson, for instance, is so unstable that it decays almost immediately after being created, close to the collision point. The particles it produces, including muons, which are relatively easy to track, have trajectories that trace back to that original collision location. So, one of the standard cuts in the trigger system is based on trajectory origin. If the detected particles don't trace back to the collision point, they get thrown away as noise. Now imagine a Higgs boson decays into dark sector particles instead. Those dark particles are invisible to the detectors. They pass right through, but they're unstable, and some of them eventually decay back into standard model particles through another portal interaction, producing muons that the detectors can catch. The problem is that this return trip takes a tiny fraction of a second, but covers a measurable distance. The resulting muons don't trace back to the collision point, they trace back to somewhere slightly displaced from it. And the trigger throws them away. The LHC has almost certainly been producing Higgs to dark sector decays this entire time, and the trigger system has been dutifully deleting the evidence, millisecond by millisecond, for years. The good news is that this is fixable. The LHC is currently offline, undergoing a major upgrade. When it switches back on in 2030 as the high luminosity LHC, it will produce 10 times as many collisions per second and is expected to generate around 380 million Higgs bosons over its extended run, 10 times more than all previous datasets combined. More importantly, the trigger system is being updated. The new algorithm will specifically look for muons with displaced origins and flag them as potentially interesting, rather than discarding them. Data scouting, recording minimal information about flagged events, and deciding later whether to store the full detail, means that even with the flood of information, nothing that looks like a dark sector signal should slip through the cracks. Depending on the strength of the coupling between the Higgs and the dark sector, evidence of displaced muons could start showing up within the first year of the upgraded collider running. It might take several years if the coupling is weak. And even a clear signal of displaced muons wouldn't immediately prove the dark sector exists. Physicists would need to map out the mass distribution of the intermediate particles, study their decay timescales, match the data against theoretical models. Science doesn't do dramatic single moments of revelation. It does slow accumulation of evidence until the case becomes undeniable. But if everything lines up, if the displaced muons appear, if the numbers match the models, if the Higgs portal holds up under scrutiny, it would be one of the most significant discoveries in the history of physics. Not just confirmation that dark matter exists, which we already know from its gravitational effects, but an actual window into a parallel particle world that has been sharing the universe with us since the beginning of time without us ever knowing it was there. All from watching a particle explode, just watching more carefully than before. If this kind of deep dive is what you're here for, you're in the right place. Subscribe and hit the bell so you don't miss what comes next, because the LHC switching back on in 2030 is going to be one of the most watched moments in modern science, and we'll be covering every step of it.